In 2021, he earned the Edward Teller Award from the American Nuclear Society, and he further from the APS won the John Dawson Award in plasma physics in 2022. So for achieving the first laboratory burning plasma as a result of the large NIF accomplishment. We'll be hearing more tonight. So it's both my honor, and I think all the officers representing the various chapters and sections in IEEE that are hosting us tonight to welcome Omar Hurricane. So we look forward to hearing what you have to tell us, Omar.
Thank you for the invitation to speak and tell you about our recent results. So I'm going to tell you about how ignition and what we call target gain greater than unity was achieved in inertial fusion. This is a collaboration over the 30 or so years from conception to the recent record results. There have been about 1,300 people involved at various aspects of the facility operations, targets, target design, experiments, and so forth. And a number of institutions are participating in the work that we've done here over the many decades that we've been working on this. So keep that in mind as I present. Okay, I'm going to start with conclusions, and these the understanding of what these mean should unfold throughout this talk. The exciting parts of our work are that the recent experiments that we've done on NIF, National Ignition Facility, using ICF, which the acronym is Inertial Confinement Fusion, they are an existence proof of laboratory ignition and target gain greater than unity. And people working in fusion have been seeking those milestones for a long time. Interesting that no mystery physics obstacles were observed on our way to ignition or gain. There were certainly skeptics and critics who were expecting some sort of gremlin out there to prevent us from achieving this, but the physics seems to say otherwise. The theoretical predictions of where we expected ignition to occur in terms of the physics parameter regime was actually consistent with our results. The parameter regime is usually called the Lawson triple product, which is a product of plasma pressure, temperature, and time. But basically, there were no surprises there in hindsight. One of the key conclusions that we had from a practical point of view, that additional laser energy at fixed power ended up being very beneficial, and I'll explain why that is later. And that's somewhat contrary to the conventional wisdom in inertial confinement fusion, where people thought higher power lasers were always what's needed, and the physics again seem to imply otherwise. So the implosion physics, and the implosion I'll describe in a bit, is a key dynamic mechanism that drives our fusion fuel to ignition conditions, ended up being a lot more sensitive to engineering control of the laser and targets than was originally thought. And that's why it more or less took us an extra decade to get to ignition. Also, so far, very high gain, which also means high compression targets, have not worked as expected. So all of the breakthroughs over the last decade have used what we call low gain designs, which are good for research and for proving concepts, but ultimately for energy production, which is, I know, what a lot of people are interested in. We need to get these high gain targets to work, and we have some understanding building to do yet. But what's remarkable and what's exciting is that we can now talk about burning plasmas, ignition, and scientific break-even in the past tense. And if you've ever heard that joke about fusion always being 20 years away, well, now some of these things are in the past, and that's quite a change. Okay, so let's talk about what we're trying to achieve to get high fusion gains in ignition. And let's start by looking at the fusion reaction rates that are commonly part of work that we do. So up on the upper right-hand side of the slide, we are most interested in the deuterium-tritium fusion reaction. And that is, the reaction rate is shown here on the plot on the left, this is reaction rate versus temperature. The deuterium-tritium fusion reaction is of most interest to us because it's actually much higher reaction rate for a given temperature than all the other fusion reaction rate fusion processes that we know of that we can do here on Earth. So it's just because it's you produce more fusion for a given temperature that makes DT much more attractive than pretty much anything else. The DT reaction rate produces a 14 MeV neutron and an alpha particle. So 80% of the energy of DT fusion comes out as a neutron. 20% of an alpha energy comes out as an alpha particle. Okay, that alpha particle ends up being important because in order to get high fusion yields, we need to create an assembly of fusion fuel that can stop those alpha particles. So we are trying to create an assembly of fusion fuel of our DT fuel that looks something like this image on the right, where we have a hot central hotspot of DT that's actually burning and creating fusion, and it's surrounded by a cold assembly of non-burning fuel. And for the experiments we do on the National Ignition Facility, the diameter of that configuration is only about 100 microns. And so keep in mind, 100 microns is about the thickness of a human hair. Okay, so by creating this assembly of fusion fuel in this type of configuration, where we are able to stop about 80% of the alpha particles inside this hot region, and only about 20% are hitting this cold fuel from the inside, adding mass to that central region. Now, stopping the alphas is key because of the way this reaction rate increases with temperature. And so here's the process that we're trying to make happen. We get our fusion fuel hot in this central hotspot. It starts making neutrons and alpha particles. If we are able to stop those alpha particles, they collide with other DT atoms inside the central region and deposit their energy inside the plasma that's actually fusing. Because they deposit their energy in that fusing region, they cause that plasma to heat up. If the plasma heats up, because of the nature of the fusion reaction rate, you get more fusion reactions out. If you get more fusion reactions out, you're creating more neutrons and alpha particles. And if you have been able to create a configuration where you can stop those alpha particles, you're able to trap their heat, and that causes the temperature to go up again, and then that drives the reaction rate up. We call this kind of stepwise process of heating and increasing the reaction rate self-heating. And that occurs if you can make the hotspot dense enough and at high enough pressure where you get a lot of collisions between atoms to cause the heat to stay in locally. And these conditions are rather extreme. In particular, the hotspot areal density of 100 grams per cc. Well, like the density of gold at room temperature is 19 grams per cc. So this is like 5 times the density of gold. The density of this colder material outside is about 10 times higher than that. And the pressures that are generated in this configuration are extreme, about 400 gigabars, which is 400 billion atmospheres, which is about twice the pressure at the center of the sun. So that's what we're trying to achieve. Now, this self-heating process, if it becomes very vigorous, we get a thermal instability loop where heating causes the reaction rate to go up, causing more heating, causing the reaction rate to go up again. And if that happens vigorously, we get ignition, and the temperature essentially goes to very high values, and you get a very rapid liberation of energy. So that's what we're trying to achieve. Okay, well, how do you create that condition? Okay, so for us, we use this process called indirect drive inertial confinement fusion, where we use X-rays to accelerate a capsule of fusion fuel to extreme velocity. So starting on the left of this image, we have what we call a target. We have a capsule inside, which is the spherical object, and the blue material inside that capsule is our fusion fuel. And it has a little cutaway here so you can see the fusion fuel. Of course, in reality, it's a completely enclosed capsule. This capsule is at the center of a metal vessel that we call a Hohlraum. The Hohlraum is actually a German word which more or less translates to hollow room. We then take our laser energy and fire it into holes at opposite ends of the Hohlraum that we call laser entrance holes, and the laser energy deposits that energy on the inside of that Hohlraum wall. Okay, so the lasers are not shot directly at the capsule. They're shot at the inside of this Hohlraum vessel. And that causes the laser energy to be converted into a bath of X-rays. And that's what the purpose of the Holorom is. It's an X-ray converter. And that surrounds the capsule with a smooth, more or less a smooth bath of X-rays. But the X-rays are pretty energetic and they cause the surface of that capsule to explode. So where you had a solid material on the outside of that capsule, it explodes in response to receiving that X-ray energy as it goes from solid state to a plasma state. And that explosion process is what we term ablation. That ablation creates pressure that surrounds the capsule on all sides. We create, in the experiments we do here, pressures of about 150 million atmospheres around the entire capsule. That squeezes it inwards upon itself, and that accelerates the capsule with the fusion fuel inside to high velocities. Because we're changing the volume of the capsule and the fusion fuel inside by rather extreme amounts, we're actually doing PDV work on that fuel that's inside the capsule, and that causes the fusion fuel to heat up and compress. We call that stage of this process the implosion. And so I'll talk a lot about implosion physics, where we go from this ablation to squeezing up the fusion fuel inside. Now, eventually that capsule runs out of anywhere to go because we're squeezing it in upon itself. So all the kinetic energy that gets acquired during the implosion then gets converted into internal energy when the capsule runs out of anywhere to go. When that happens, you get a rapid increase in temperature and pressure, and that phase of the dynamics we call stagnation. And if we've arranged things correctly, we get that self-heating process to become a thermodynamic instability, and you get an explosive increase in temperature and pressure and fusion yield liberated. So that's the general process that we're using to achieve those conditions and getting that thermal runaway effect described earlier. Okay, so let's talk about some terms that are often confused with each other, but actually mean something physically different. And this is just to kind of clarify some things that were in the press, and also so you can better understand our results. You often hear the terms burning plasma, ignition, and gain used interchangeably. They're not. Burning plasma actually means that the self-heating energy of that alpha heating process is exceeding the PDV work that we put in to initially heat the fusion fuel to fusion conditions. And so that's a tipping point where one heating mechanism internally out races the PDV work that gets things started. Ignition is when the self-heating power actually exceeds all the DT plasma power losses that go on as we're trying to get it hot. So you just imagine you try to get anything hot, it starts to radiate energy, it starts to conduct energy away by thermal conduction. And in our case, because we're using an implosion and generating these extremely high pressures, that implosion eventually becomes an explosion, and that takes energy out of the system. So when we're igniting, it means actually the self-heating power of the fusion reaction is actually outracing all of these potential energy loss mechanisms. And that's how we actually get thermodynamic instability. And then target gain means something a little different. It actually means the fusion yields that are generated are actually exceeding the energy that was put into the system. So these all mean something a little bit different, but again, they tend to be conflated with each other. Another confusion comes with target gain because a committee in 1997 from the National Academy of Sciences actually defined ignition as target gain, and that just contributed to more confusion in a lot of the government documents. And here we are. Okay, so how do we get these implosions to actually operate and bring our fusion fuel to ignition conditions? We have a gigantic facility, such as the National Ignition Facility, which is what actually drives everything. The National Ignition Facility is the largest laser facility on the planet. The diagram showed here is, if you will go out to the facility, it's about the size of 3 football fields put side by side. Let's talk about some of the elements of this facility here. On each side of the facility, we have two bays of 96 laser beams each for a total of 192 laser beams, which are driving our experiments. These laser systems are driven initially by capacitor banks here on the sides of the facility. These capacitor banks are charged with electrical energy, and about 300 to 400 megajoules of electrical energy go into those capacitors. Those capacitors then dump their energy into laser preamplifiers, which are at the upper left side of the slide here. And that is where the laser starts off. The preamplifiers feed laser light into main amplifiers that pass the light back and forth, picking up energy from flash lamps as the light bounces up and down the beam lines. As those laser beams pick up energy from the flash lamps, they eventually acquire 3 megajoules of energy total. And the light is in the form of what we call red light. It's 1 omega, which refers to the frequency of the light. And that is the light that ends up being shot towards the target chamber. So on the right side of this slide, you see this periscope arrangement of pipes that take the light from the main laser bay, reflect it using mirrors towards the target chamber, which is shown on the right. And red light is passed right up to the very edge of that target chamber. As the light is about to enter the target chamber, it passes through a system of optics that we call the tripler. The tripler converts the 1 omega red light to 3 omega blue light, and that's that blue light that ends up being shot towards the target that will be at the center of the chamber. So 2 megajoules of blue light is actually shot towards the target. The target is at the center of this target chamber, which is about 10 meters in diameter. And the target itself, our fusion target, that Hall-ROM, which I was talking about earlier, is shown here on the upper right, and it's juxtaposed with human fingers, so you can see the scale. It's about 1 centimeter in length. And so 2 megajoules of blue light enter that Hall-ROM through the holes at the top and bottom. Inside that Hall-ROM is our capsule that we described in the cartoon earlier. And again, juxtaposed with the human finger here to show the scale. That capsule is only about 1 millimeter in radius. Because of this large difference in scale between the Hall-ROM and the capsule, that bath of X-rays that's created only deliver about 250 kilojoules of X-rays to the surface of that capsule, and that's what gets absorbed. Of course, the capsule has the fusion fuel inside of it, and because most of this capsule is turned into a plasma through the ablation process, only about 20 kilojoules of the energy actually make it into the DT fuel. So what's the point of this is actually we start with 300 to 400 megajoules of electrical energy, and we only end up with 20 kilojoules of energy in the fusion fuel. So there's a huge loss of energy going from the capacitor banks to the fusion fuel by going through this process of using lasers to drive a Hall-ROM, to drive a capsule, to squeeze up the fuel. That is the way inertial fusion works, however. We sacrifice energy to make energy density. And we need to make the energy density to get materials compressed enough so that they can achieve a lot of collisions when these alpha particles are produced and trap the energy in the fusing region to get that explosive instability that we want. So most of the initial energy is lost before it ever gets to the fusion fuel. So for practical fusion, you actually have to make that up, and that's why ignition is key. All right, so because there's such a large cascade of energy going from the capacitor banks to the actual fusion fuel, when you talk about gain, which is energy out versus energy in, it's natural to ask, energy out of what, energy into what? And for those of us who work in this field, we have several different definitions of gain that we use that are defined for different volumes of our target system. So again, here's a picture of our target on the right. We have the outermost part of our target, which is the Hall-ROM. And the gain associated with that is the target gain, which is a measure of the fusion yield that comes out over the laser energy shot in. Inside the Hall-ROM is the capsule. which is the spherical object that does the ablation and squeezing up of the fusion fuel. So you define a capsule gain, which is the fusion energy out of that volume as compared to the X-ray energy absorbed by that surface. Inside the capsule is the fusion fuel. And so you can define a fuel gain, which is the fusion energy out over the energy that actually ever made it into the fusion fuel. Okay, well, over the last decade of work, we've been able to push all of these gain values up by a factor of 1,000, or actually a factor of 5,000, as shown in this plot on the right. So this is log-log scale plot. I'm showing fuel gain essentially versus a parameter that we call the generalized Lawson criteria. It's a parameter that involves the plasma pressure of the fusion fuel at peak compression, the time duration over which we're able to hold that together, the temperature of the fusion fuel, and a little metric that has to do with the energy that was in the cold fuel versus the energy in the central hotspot. Anyway, if you plot fusion gain or fuel gain against this metric, basically all of our data fall on a single curve. And as I said, starting from 10 years ago to now, we've increased that gain by a factor of 1,000. We first achieved fuel gain back in 2014, where we finally got more fusion energy out of the fuel than we put into the fuel. In 2021, in August 2021, we finally got more fusion energy out of the capsule than we put into the capsule. And then the most recent result, which was in the news back in December, is where we finally got more fusion energy out of the target than we put into the target. And as of December 5th, 2022, these different gain values are shown here. We have a target gain of 1.5, a capsule gain of 12, and a fuel gain of 160. So we are getting a lot more energy out of the fuel than we put in, a pretty respectable amount of energy out of the capsule than we put in, and a modest increase on the amount of energy we put into the target than we put in. But because the facility consumes so much energy, it's important to recognize that all of these gains being greater than 1 does not mean we're making net energy from a useful, want to power my house point of view. These are great kind of scientific milestones that we've achieved, demonstrating the principles. But this, the National Ignition Facility is a research facility, not a reactor, and we aren't going to be putting energy on the grid anytime soon. Okay, so let's talk about why it took us 10 years to move those gains up by a factor of 5,000. Why didn't it just work initially? And there are 5 key problems that we had to overcome in order to make things work. The key topics are instability control, I mean hydrodynamic instability control, symmetry control of our implosions, sufficient energy coupling to the fusion fuel, target quality, which is an engineering problem, and we have this high compression problem, which is actually still a problem we have today. Okay, so we have some levers on controlling our implosions through something we call the laser pulse shape, which is the temporal profile of energy versus time that we request from a laser. And I'm going to talk about this briefly, just so you can understand some of the key aspects of making an ICF implosion work. So in blue, I have laser power versus time. This is shown in terawatts for a typical experiment that we do. And there are 3 parts of that laser pulse that are key to making an ICF implosion work and controlling some of those issues I mentioned on the previous page. The 3 key elements of this laser pulse that allow us to have some ability to control our implosion are the early part of the laser pulse, which we term the foot. I'm telling you this so you understand some of our jargon as well. So the early part of this laser pulse is the foot. This initial bump in energy we call the picket. This part of the laser pulse actually controls hydrodynamic instability of our implosion and the majority of the entropy of the fusion fuel as we try to compress it up. We term that entropy adiabat, and it's denoted by a parameter that we call alpha in flight. So this part of the laser pulse kicks things off. The rise to peak power actually controls the implosion velocity. That is where our implosion acquires most of its kinetic energy from. And then the late part of the laser pulse ends up being important for converting that kinetic energy that the implosion acquired into internal energy at stagnation. And a key part of this jargon is called the coast period. So it's the duration between when we turn the laser off and when the implosion actually gives up most of its fusion energy. So the reason why this pulse shape can actually have some influence on the implosion is because of this Hallrum that we're using, where that we don't point the lasers directly at the capsule, we point them at the Hallrum, and we create this X-ray oven. When we create this X-ray oven, there's a temperature associated with that X-ray oven, and we call that the radiation temperature, and that's what's shown in red here. That X-ray, that radiation temperature is important because the ablation pressure, which is actually what's squeezing the capsule inwards upon itself, depends on a high power of that radiation temperature. So this radiation temperature is almost like the energy or a temperature that you would have in a normal oven that would have IR radiation that you feel if you stand next to an oven when you try to break bread or something. But in this case, it's X-rays. That every temporal change in the radiation temperature as a function of time causes an increase in the ablation pressure. So when we put laser energy in at early time and we cause a jump in radiation temperature, that corresponds to a jump in pressure, and that launches a shock wave into the implosion. And every time there's a little kink in that radiation temperature, we launch additional shock waves in. And it turns out we can control stability and compression with those shock waves. There are other properties of the ablator that matter for the ablation pressure: the atomic number, the atomic mass, and the albedo, which is the tendency of the ablator to reject X-rays as we try to squeeze up the implosion. Okay, so the laser pulse shape is kind of the key tool that we use to control many of our implosion properties, but it's not a perfect tool. So in 2010 to 2012, we were using plastic ablator capsules with a laser pulse that we call the low foot. And those low foot implosions actually had a very low picket at early time with very little laser energy going in. And they were designed to actually produce very high fusion yields, but they actually ended up underperforming. So I'm going to be showing you some plots here to walk you through the story of fusion yield versus temperature in terms of number of neutrons, and this side of the plot is fusion yield in kilojoules versus pressure. And we're going to see how things improve over time as we got better control of the situation. Okay, so but these early implosions, which were part of what we called the National Ignition Campaign, didn't perform at all like expected. And there's very little correlation between the fusion yield and the pressures. The fusion yields were about an order, 3 orders of magnitude low compared to what the original projections were. And it really nearly ended our program at that time. And so we had to sort out what was going on. The first conjecture that we had was that the hydrodynamic instability associated with fluid motions that occur when you have interfaces between materials at high accelerations was challenging the ability of these implosions to perform correctly. A movie basically illustrates this process most directly. So here is a implosion from that low foot series. This is a simulation done by a colleague, Dan Clark. I'm going to show you temperature on the left and density on the right. You can see there are already some small wiggles in the surface that occur at peak velocity, and you're going to see them amplified as the implosion proceeds. Okay, so now let's back up. So as you saw in some of those cartoons I drew earlier, we actually are trying to achieve a hot spot in the middle surrounded by cold fuel. I mean, that's the way the ICF implosion is supposed to work. Most of the fusion is going on in here. But if the implosion becomes too hydrodynamically unstable, it tends to turn itself inside out. So we no longer have a hot spot in the middle. We no longer have a smooth configuration of fuel on the outside. and that is a consequence of Rayleigh-Taylor instability. What's happening here is that we have interfaces between materials of different density, and because we're accelerating them, there is a property of Mother Nature where she wants to amplify small perturbations between these materials and make them large perturbations exponentially in time. And that process is pretty ubiquitous in nature, and it's a challenge to making an ICF implosion work. The way we can compensate or try to manage this tendency of Mother Nature is by a couple of terms that show up in the growth rate for ablative Rayleigh-Taylor instability, which is shown here on the upper left. So we have the unstable drive, which goes as the square root of the wave number of these perturbations, which is related to the wavelength, and the acceleration. That's the Rayleigh-Taylor drive. But because we're evaporating off or ablating off the outer surface with these X-rays, there's a stabilizing term having to do with the rate at which material blows off. And there's a stabilizing term having to do with the density gradient scale lengths associated with just the physical rate at which densities vary in our system. So we can compensate for Rayleigh-Taylor instability by increasing the ablation velocity and by increasing the density gradient scale length. And we hypothesized at the time that the low foot implosion wasn't working, that we needed to control those things better. That led to the idea of a high foot implosion where we would increase both of these stabilizing terms and not eliminate the unstable growth, but lower it. And that led to a set of experiments called the high foot experiments, where we better controlled hydrodynamic instability to improve performance. And those, if we look at the fusion performance of those experiments, they did indeed do better. We were able to increase the fusion yields by a factor of 10, the temperatures by a factor of 2, the hotspot pressures by a factor of 3, finally exceeding the pressure at the center of the sun about partway through these experimental series. Again, the pressure at the center of the sun is between 200 and 250 gigabars, billion atmospheres. So those were successful, and they showed indeed that the hypothesis that Rayleigh-Taylor instability was frustrating the low foot implosions was probably correct, and that by managing it better, we could do better. Because we were able to manage these implosions better and get good results, or reasonably good results, we did a series of experiments to test the repeatability behavior and see what else we could learn from these implosions. We did a series of experiments where we tried to repeat the implosions several times and see if we more or less got the same result. This table here shows what those implosions look like. So we have a series of experiments here at intermediate power and energy, 350 terawatts, 1.6 megajoules, and at higher power and energy, 390 terawatts and 1.8 megajoules. You're looking at X-ray emission from the fusing region. You're actually seeing the brightness as time integrated as the fusion proceeds. You can see that there is some repeatability in the shape of that emission. We have neutron imaging showing the 14 MeV neutrons that come directly out of the fusing region, and the blue glow is how those 14 MeV neutrons scatter off the surrounding cold fuel, giving you some idea of the morphology of the cold fuel that's surrounding the hot spot. Yeah, there's some repeatability here. In terms of fusion yield and temperature, there's pretty good repeatability. The only exception is for this experiment here, we had a laser misfire where you can see the shape and the yields and temperature are considerably different. So because we had repeatability, we could use those experiments to learn some things about implosions and other knobs that we could use to get performance, better performance. One of the knobs that we explored was this idea of coast time, which is how we turn the laser off, which was something that really wasn't a priority or really thought important before we started doing these experiments. So here's a plot of laser power versus time. We have 3 experiments, a baseline experiment in blue, and then 2 variations on that where we increase the power and turn it off early in green, and another one where we keep the power on for a long duration of time and then turn it off later. So the green one has a long coast time, and the red one has a short coast time, and we wanted to explore what that did. So if we did experiments with these variations and inferred the stagnation pressure at the center of our fusing plasma, we saw that when we reduced the coast time, even though we lowered the power, we got higher pressures at the center of our implosion. And we decided when we saw that we'd proceed to explore continually lowering the coast time and watching the plasma pressure go up. And that's actually what happened. So by reducing the coast time, we could see a great increase in plasma pressure. And we knew that this duration was a lever, indeed a lever, on how our implosions performed. The reason why it ends up being important is due to two factors. One has to do with the Hall-ROM, where again, the laser power is translated into radiation temperature versus time. And when we had a lower amount of power for a longer duration of time, it means our X-ray oven stayed hotter later in time. And that was beneficial for our implosion. And the reason why it was beneficial had to do with the radius at which the implosion acquired its peak velocity. So by having the radiation temperature higher later in time, we continue to push on the implosion later in time than would have happened otherwise. And that means the implosion acquired its peak velocity at a smaller radius later in time. But as we said earlier about what a stagnation process is, and eventually the implosion runs out of anywhere to go, so that kinetic energy gets converted to internal energy. So this behavior implied that the later in the implosion acquired its peak kinetic energy, the better the conversion of that kinetic energy would be converted into internal energy. There's a mechanical analog here having to do with race cars, which is maybe easier to understand than everything I've just explained. And it's the term is called late braking. If you're driving your car on the road, it's an object with mass and it has velocity, so it has kinetic energy. The way a normal person drives is you see a turn that you're coming to, you start putting on the brakes gradually, and you gradually slow down the car before you come to a turn, and then you pass through the turn and then speed up again. If you're driving a race car, because a racer wants to spend a minimal amount of time in the corner so he can win the race, you're taught to do what's called late braking. So you race as fast as you can right up to the turn, and then you push very hard on the brakes, and then you pass through the turn and leave. What happens in late braking is you're taking the kinetic energy of the car and you're turning it into heat on the brakes. And in racing, you actually see the race car brakes glow because you're converting all that kinetic energy into heat in the brakes. And the brakes don't have enough time to dissipate the heat. And so that's very hard on the brakes and on the tires. But that's the way a racer is meant to drive. And that actually ends up being the analog of what's happening in our ICF implosions. If we can rapidly convert the kinetic energy it's acquired through the ablation process into internal energy, it doesn't have as much time to cool off as it would have if we would have slowed it down more gradually. So, and that's really what the physics of coast time is, and that's why it ends up being important. It doesn't give the heat a chance to get out. All right, so because of that series of high-foot implosions showing that this coast time was useful, but we still saw asymmetry being an issue, we needed to find another tactic to continue to push the performance of these implosions up. And so in 2015 to 2018, we switched to a different ablator material called HDC, which is a euphemism for diamond. It's industrial diamond. And we also switched our Hall-ROMs from high gas fill Hall-ROMs to low gas fill Hall-ROMs. The reason why the high density carbon was important is it allowed us to, it has a density of about 3 times that of plastic. So because the density is 3 times higher, we could make the ablator 3 times thinner. And that allowed us to make the pulse shapes of our laser requests shorter. And we thought by making the pulse shapes of our laser requests shorter, that we could better control symmetry of our implosions. And that's why we ended up trying this tactic. So by switching to these materials, we were indeed able to increase the performance, the fusion performance by a factor of 2, and increase the pressures we achieved in the fusion region by a factor of 2. But you can see here that the fusion performance again saturated out, even though we tried to continue to push to higher levels. And it turns out, while we improved some of the symmetry that we saw in those earlier high foot implosions, we were still being challenged to control the symmetry as good as we really needed it to be. So this slide here shows some of the zoology of the different asymmetry problems that we've had on a variety of implosions. The upper set of images are neutron downscatter images that show you the morphology of that shell of cold fuel that's supposed to be surrounding the hot spot. Again, it should be a uniform thickness round shell. You can clearly see it's not. We have in the second row are synthetic data images from simulations matched to these experiments, and the bottom row are density and temperature images that come directly from the simulations which you use to model these experiments. So you can see there's quite a variety of morphologies that occur in our implosions. They're not perfectly round like the cartoons we draw and that we'd like to have. And this is a problem, and I'll explain why it's a problem now. It's more than just it looks funny. As I tried to emphasize earlier in the talk, we get very little energy from the capacitor banks and the laser into the fusion fuel. So energy is really precious to us. And it turns out asymmetry is related to energy. So when you see asymmetry, it means you're wasting energy, and that'll make more sense in a moment. Energy is important because we knew from our database of experiments, and that's shown here on the left, that neutron yield, the fusion yield, actually went up as a high power of the energy that we're actually able to put into the hotspot. So here we see a set of experiments from 2012 to 2018, where the yield is basically going up as the third power of the energy that makes it into the hotspot of our fusing region. So we obviously want as much of that as we can possibly get. At the same time, we had been doing simulations for years, like the ones I just showed on the previous page, that showed that when you had asymmetry, the fusion yields would go down. And the mechanism behind why asymmetry would cause the fusion yields to go down was not really understood well, but it certainly was exhibited in all the simulations that we did. And that's what's shown here on the right. We understood later that asymmetry, energy in the hotspot, and kinetic energy are all connected through this relation here shown on the middle center of the slide. The hotspot energy is basically related to the kinetic energy of the imploding shell, where m is the mass of the shell, v implosion is the velocity, the peak velocity that the shell acquires. And then you have this term that's a measure of asymmetry that we call now RKE, residual kinetic energy, or normalized residual kinetic energy. So what we want to do, if we want to get a lot of fusion yield, we want to maximize kinetic energy, but we want to minimize asymmetry. Because of that instability control problem we mentioned earlier, the way we want to increase kinetic energy is not by increasing velocity any more than we already had, because we would need more accelerations, which would be more a tendency towards instability. So we felt, well, the only way we're going to be able to further increase the kinetic energy was by increasing the mass of the shell and basically leaving the implosion fixed, but we can't allow any asymmetry, or we have to minimize the amount of asymmetry we had if we want to maximize this quantity. So this strategy that involves making the mass of our implosion, our shell of the implosion, as massive as we could while controlling the asymmetry as much as we can, we call the hybrid strategy. That stands for high yield big radius implosion design. And that was the strategy we followed from 2018 onwards. Let's take a moment to understand why asymmetry is connected to energy, however, because this could be understood with some pretty basic physics in hindsight. And it's kind of funny that it took so long to figure this out. So instead of that complex morphology of those asymmetric implosions that I was showing coming from the simulations, let's think of a simple abstracted implosion where we have hot fusion fuel trapped between two pistons, like in pistons in an internal combustion engine, and those pistons are flying towards each other at some velocity called the implosion velocity. And the gas follows a simple equation of state that pressure times volume to the gamma 5/3 is a constant. Okay, so those pistons are flying towards each other and they're going to squeeze up the gas. If those pistons are exactly the same mass and have exactly the same velocity, you have a symmetric situation, and they squeeze up the gas and they transfer the kinetic energy of those pistons to the gas, making the gas hot, increasing its density, increasing its pressure. But if those pistons are asymmetric, either in thickness or mass or velocity, you get a net center of mass motion. So this is a pretty simple mechanical system. You can actually write down conservation and conservation of energy and conservation of momentum to figure out what the pressure of the gas is. And you do the math and you find out that the pressure is again related to the kinetic energy, mv squared of the pistons. But there's this degradation term having to do with the velocity of the center of mass motion that basically works against the kinetic energy that you're trying to put in. This center of mass motion, because of conservation of momentum, once you have a net center of mass motion, that kinetic energy of the center of mass never goes away. And that is what this wasted residual kinetic energy is in this simple system of a 1D arrangement of pistons. Now, this really seems like a simple mathematical cartoon of an implosion, but actually it ends up matching our simulation database and our database of experiments very well. And so that was kind of an insight that really helped us understand why asymmetry was connected to energy and why we really needed to fix it. You can generalize that simple mechanical picture to a higher dimensional version to deal with all other forms of asymmetry. The math becomes more complicated, but it's not really important to go into. There's an interesting geometric average that we call the weighted harmonic mean that has to do with the inverse of the areal density and the areal density in this funny set of equations. But again, that residual kinetic energy ends up being related to geometry in this case. So when you see asymmetry, it's interesting that in an implosion, geometry is a reflection of energy. And when you have asymmetry, it means it's a reflection of wasted energy. And this physical picture actually matches our simulation database very well. You don't have to be an expert. You can see that this implosion is more symmetric than this implosion, and residual kinetic energy is increasing as you go up. So geometry in an implosion, or asymmetry in an implosion, is a reflection of wasted energy. So you got to fix that. So we had some idea of how to control asymmetry in our implosions by pointing our laser beams through that laser entrance hole in different directions. And by pointing those laser beams in different directions, the region where they convert to X-rays gets moved depending on where you point them. And you could, in principle, control the sky of X-rays that's surrounding our implosion, causing it to squeeze up upon itself, and in principle, give a uniform implosion. What we realized in the 2015 to 2018 period is that our laser beams tend to interfere with each other through the plasma that they're making off the Hall-Rahm wall. So where we had a set of beams that we call the outer beams hitting the gold wall from our Hall-Rahm that we'd cause a plume of plasma to fly inwards up into the Hall-Rahm, and that would interfere with other laser beams that are trying to propagate in. And it wasn't until this period where we were able to assemble our data in a way that made this problem clear, where we saw that the asymmetry, and particular what we call a mode 2 asymmetry, which is a tendency to basically either be a pancake or a sausage, was directly correlated with the amount of energy that we shot on these outer beams and the ingress of this gold plasma inwards. So if you write down the physics of this gold bubble expanding inwards, it basically goes as the sound speed at which that plasma ingresses. That goes as the square root of the energy that entered that bubble over the density. There's also the area of the laser spot involved. The time duration over which you allow that to ingress in increases the effect it has on interfering with the inner beam. And then there are a few other parameters having to do with the geometry, the radius of the capsule, radius of the hologram, and so forth. In other words, we were able to infer from our data that if we could control this parameter, we could control the asymmetry. And this was a key insight that came from colleagues Debbie Callahan and Joe Ralph. And that if we just looked at things in terms of the right parameter, we would be able to bypass this problem. The other physics that we learned during this period is that we could use cross-beam energy transfer in these low gas fill holograms to move energy between the outer laser beams and the inner laser beams and force more energy onto the inner laser beams. And that allow us to fine-tune the symmetry of our implosions if we couldn't kind of get the right ballpark behavior by using the scaling. So two key insights. One, understanding the physics of what was frustrating our symmetry, and one, recognizing an additional tool that we could use to control asymmetry allowed us to get past these problems. So we then thought we understood everything that we needed to do to implement this hybrid strategy. We understood that we needed more kinetic energy by increasing the mass of the implosion, the shell, which you can increase by making the radius larger or making it thicker or doing both. When you do that, we understood how to control the asymmetry better and not get it to kill us. And so we tested that strategy in the 2018 to 2020 period. And initially, that strategy actually struggled. We didn't really see an increase in fusion yield. We really didn't see an increase in hotspot pressure. And that put our program under a lot of scrutiny for those 2 years. What had happened during this period is when we scaled up our capsules to larger size, we were surprised by an engineering problem that cropped up having to do with the quality of our capsules. And that's illustrated here. Again, here's another cartoon of our hologram with our capsule inside. We're taking our capsules and making them bigger. When you normally think about defects in any manufactured object, you don't think of the defects actually getting worse when you make it bigger. There's no reason for them to get worse. So we actually thought by making things the target bigger, it wouldn't make the engineering defect problem any worse, but in fact, all of us were surprised by the defects becoming worse. So the defects that we observed in our shells, so here's a cutaway, an X-ray image of the through thickness of the shell. You see a number of different voids that are appearing in the through thickness of the capsule. If you look at the surface of the capsule, it looked like the surface of the moon. Sometimes there were big holes hidden in the through thickness. And the reason why all of these matter so much is because they all become seeds for hydrodynamic instability as the implosion proceeds. So here's an example. This is the central hotspot emitting X-rays. This is data that you're looking at here. And then you're going to see something fly in from the left. And that is one of these defects being amplified by the Rayleigh-Taylor instability drive into a jet of material that enters that hotspot and damages it. The reason why that these defects cause damage when you get jets of material entering the hotspot is a reflection of the fact that materials, as they get hot, they tend to want to radiate X-rays away. And the higher you are up on the periodic table, the more efficient materials are at radiating energy away in the form of X-rays. So on the right of this slide, you see, again, kind of a simulation cartoon image of our central fusion core. Its density on the left, its temperature on the right. We're trying to get this hot DT in the middle. The processes that are competing with each other that make the fusion fuel temperature increase are the alpha heating, which goes as this is in power, energy per unit, time per unit mass. So it goes at the density times the reaction rate. We want as much alpha heating as we can. Again, when you make anything hot, thermal conduction takes energy away. That goes as a high power temperature over the areal density. And then it radiates X-rays, and that goes as the density times the square root of temperature. The prefactor here on this X-ray loss actually depends on the atomic number. So if you have DT, which are isotopes of hydrogen, the atomic number, the Z bar is 1, the average atomic number is 1. But if you have higher atomic number materials, the Z bar increases. And when the Z bar increases, that means you get more radiation loss. And when you get more radiation loss, that means you're losing energy. But again, we tried to emphasize that energy is precious because we get so little energy into our fusion fuel in the first place, we really can't afford to lose it. So the consequence of losing energy to X-rays is illustrated in this plot of yield amplification, fusion yield amplification versus kinetic energy. And if we had a situation where we had a perfectly clean fusion fuel with just DT, that's shown in blue, we get the rapid increase in fusion yield when we get to a certain level of energy, that's ignition. But then now we add materials that are higher up on the periodic table to the fusing region because of defects from the capsule being injected in. We call that mix. You see that curve move to the right. And if you get more mix, you move further to the right. So essentially, there is an energy cost having to do with radiating energy away that now you have to make up for, almost like asymmetry. And that's why all these capsule defects matter, because when they seed instability and they get injected into the fusion fuel that you're trying to make hot, they tend to want to cool it off again. And ultimately, that costs you energy. And again, we get so little energy into the fusion fuel, it can be a make or break situation. So we can't really tolerate that. But after years of effort, their target engineers were able to address some of those target fabrication problems. And our laser engineers were able to squeeze a little bit more energy out of the NIF laser. We were able to go from 1.9 megajoules to 2.05 megajoules. And just fortuitously, we had good capsule quality at the same time, and that enabled our most recent success. So now if you look at the fusion yield versus temperature, we've gone up by another order of magnitude in fusion yield, and we're now making those several megajoules of fusion yield that were originally envisioned over a decade ago. So the story is kind of a story of not some super innovative idea, silver bullet that basically solves all problems. The story I'm trying to tell that we addressed problems in steps, and we kind of used a basic principles understanding to understand what was going wrong in our experiments, and then figuring out what we needed to do to fix it. And we had to repeat this process over and over and over again over the period of a decade to get a factor of several thousand increase in fusion performance. Of course, a considerable amount of design optimization and finesse was required as well to make this 3 order of magnitude jump. Okay, what actually ended up working and all the record results from the last 2 years, the concept we actually called hybrid E, which again is that high yield big radius implosion design, but there was a hybrid B, there was a hybrid C, there was a hybrid D, and then finally an E. And the E is the one where everything worked finally. And I don't have, there's no time to go into the other previous versions. But this was the first design and concept that actually achieved burning plasmas and ignition in the laboratory. A picture of what it looks like is shown here on the left. Again, it's the same cartoon as we've been showing for years, but the details of the dimensions are different, and the details are important to making these things work. The associated laser pulse that makes it work is shown in the middle of the screen. The key elements of the design that worked were using a design that had a 20% larger capsule radius than previous HDC or diamond ablator designs. We reduced the size of these laser entrance holes. We learned how to control symmetry when we reduced the size of these laser entrance holes, and we used that crossbeam energy transfer to keep the symmetry good as we did that. And that minimized the amount of X-ray energy escaping, again, trying to minimize the energy losses in our system. We again use that trick of coast time, where we lower the laser peak power, but we extend the duration of peak power to maximize the conversion of kinetic energy into internal energy. And all of these resulted in increased hotspot pressure and energy. The two record designs from the last 2 years are shown here. You're looking at neutron images, neutron emission images from the two record performing experiments. The one on the left is our 1.4 megajoule experiment from August 2021. You can see, again, it's roundish, but it's not perfectly round. And then the most recent result from December 4th, 2022, it's quite round, and that one gave us the 3.15 megajoules of energy. Basically, the only difference between these two experiments is the one on the right had the 8% thicker ablator, increasing the mass of the shell with the 8% more laser energy than this experiment here on the left, and with the appropriate improvement in symmetry control. The laser pulse between those two experiments, again, very similar, and it was just this extended duration of keeping the laser power on a little bit longer to get a little more energy out and continue to reduce the coast time is what the trick was. So this is a story of incremental success by evolutionary improvements. At this point in time, we have about 4 experiments. We have 4 experiments that have actually ignited by passing the Lawson ignition boundary, which is that pressure, time, temperature curve shown here in blue. We have 1 experiment that has actually achieved target gain greater than unity, and we hope to repeat that experiment sometime soon. As I mentioned earlier, this whole 10 years has been kind of a plan B for the original strategy, which was to use high compression implosions. We still have this problem where we don't actually understand why we are frustrated by Mother Nature when we try to go for high compression implosions. It's illustrated in this plot. We have measured compression here on the y-axis, the adiabat on the x-axis, a theory curve shown in black. And as you can see, most of our experiments that we've done, the compression that we actually acquire or get in experiment is much lower than the theory. We have a few cases where we actually do get compression consistent with the theory, but then those implosions didn't perform correctly. Those were the low foot implosions that I mentioned at the beginning of the talk. So this is a frustrating problem that we don't understand, and it forced us into a different strategy where we used low compression targets or designs to make progress. Eventually, though, this problem has to be solved, because if you want high DT fuel burnup, you need high compressions. The efficiency of burnup is directly related to the areal density, and the areal density is directly related to how much compression you can achieve. So if we can't get this fixed, we'll forever be stuck with low efficiency targets that really aren't appropriate for inertial fusion energy interests. Okay, but again, we're doing science at the laboratory here. We're just trying to prove principles, and we're still working on this stuff. And what is remarkable, again, is that we can now talk about burning plasma's ignition and scientific break-even in the past tense. That's the real accomplishment. And the other bullets repeat the conclusions I had at the beginning. Again, we've seen that there are no mystery physics obstacles standing in the way of ignition or gain. We've gotten both, so it's proof by example. The theoretical prediction of where we should get ignition has been proven out. This trick of using additional laser energy, reducing the coast time, has been very beneficial, and it's just funny that was kind of an ignored topic in the field for a lot of years. And as I've tried to emphasize, our implosion physics is super sensitive to engineering control of the laser and targets, much more so than we originally thought. And this is because this nature of an implosion is actually to be an amplifier. We want it to amplify pressure, which is its fundamental purpose, but it also amplifies things we don't have perfect control of, like the symmetry or the target quality. So little defects become huge problems as an implosion proceeds. Okay, so far we haven't been able to get high compression to work, and we really need to get high compression to work for useful fusion energy using this type of technique. And all the breakthroughs over the past decade have used low gain designs. So with that, I'll stop. I'm a little over an hour, so I can take questions that people have.
All right. I don't see questions yet in the chat.
Can we ask them verbally?
Yeah, I see there's, let's see, I see, could you turn on closed captions? Oh, it's too late for that.
I wasn't able to do that.
Should use your slide 18. So. Oh, yeah. Oh, okay, Sam. That's right. That's yeah, one of your one of the retirees is part of the Porsche Club of America. And he and I both like doing track days together. So we're both into this idea of late braking. And I don't have a picture of my car glowing the brakes.
Because that's a Ferrari, isn't it? Not a
That's
Porsche?
a Ferrari. That's not a Porsche. Yeah. Yeah.
So Omar, it looks like, you know, extending the laser pulse is kind of important. I think they used to say it all comes down to that frequency tripler at the end, right? That's kind of what's limiting for the 192 beams we've got. Are there? What if you just went for broke and said you didn't mind, you know, if you ruined all the triplers? Would how much could you extend out that?
Yeah, so actually we there's a plan. You know, this 2 megajoules of blue is approximate. It's really, for most of the last 10 years, it's been 1.9 megajoules. As I said, we recently pushed it up to 2.05. By the end of the summer, we plan on pushing it up to 2.2 megajoules. And the laser engineers, the chief laser engineer in particular, Jean-Michel Denicola, thinks that's possible. And there's ultimately a plan to keep pushing it up in those kind of increments of 0.2 megajoules up until about 2.7 megajoules. So eventually we'll get this up to 2.7 megajoules, hopefully. And that will allow us more flexibility in the design, and eventually that extra energy will cascade down into the fuel. So we should be able to either get higher fusion performance, which is kind of the primary goal, or certainly more robust behavior. It also, when you have more energy, it actually relaxes the engineering constraints on the targets. As I tried to communicate in the talk, it all kind of comes down to energy. If you have defects in the targets, it costs you energy. You have to make up for that somewhere. If you have asymmetry in your implosions because you can't control things as well as we'd like, that costs you energy. So you have to make it up somewhere. So by adding more energy in, it relaxes on how it relaxes the constraints that we have to put on our target fabrication control or the laser symmetry control. And that just allows us more design flexibility. Ultimately, if we have great targets with no defects, we have great symmetry control, and we have more energy, that really, we should be able to get a fair bit higher fusion performance out than what we have presently. And then we have the science problem of trying to really understand why the super high compression tactics don't work like we expect, and understand their origin and hopefully mitigate them when we do understand them eventually. And then we should be able to get really orders of magnitude more fusion yield out in the future. So what else can I say? When We did actually try doing one of these higher energy tests back in 2018. Actually, when we first started with the hybrid strategy, we actually had planned in the summer of 2018 to shoot 2.1 megajoules of energy. But the laser teams doing tests with the laser without any fusion target in the center of the chamber, doing offline tests, found that there was an unexpected instability in the laser having to do with filamentation on what they call the wedge focus lenses, which they term wiffles. And it's basically the lenses are thinner in the middle and thicker at the edge, and the laser would tend to filament at the edge and actually damage the optics. So our original attempt to do higher energy shots to test that hybrid strategy had to be called off because we couldn't afford to basically break the whole laser. Since that 2018 time, the engineers inspected why we got that instability. Some of it had to do with they discovered that dirt was getting into the optical path of the laser, and they had to seal things up better than were originally part of the design. And they actually had to put shields on the edge of the laser. They have a name for them. I'm kind of a little foggy at the moment. I can't remember what they are, to protect that thickest outer edge of the laser to allow the experiments that we did recently to proceed. So so that's kind of the story there.
Omar? This is Jeffrey. May I ask two questions? First of all, I noticed in one of your plots, you showed that an instability keeps increasing in amplitude. And it looked to me like an oscillator, in other words, a positive feedback circuit.
Is it this one?
Yes, this one.
Yeah, okay, so Rayleigh-Taylor instability, depending on the sign of this term, a square root of a positive number is a positive number. That gives you a growth rate, and it's really the integral of this growth rate versus time that grows exponentially. So this axis here, the x-axis in this plot, that's actually a spatial axis. And it's the different colors here is the time. So basically, I'm trying to illustrate here that these small bumps on our implosion grow into big bumps exponentially in time due to this hydrodynamic instability forcing. And it's usually either exponential growth or oscillation, depending on the sign of this term. If it's the square root of a negative number, it becomes an oscillator.
Yes.
And that's, think of, air and water. If you have air above water and you start the surface oscillating, that's a stable Rayleigh-Taylor situation because the air is lower density than the water and the gravity is pointing down. So the water will just oscillate. If you flip the two, if you put the water above the air, then they want to change places. And that's where you get unstable growth. And, that particular type of instability of a layer of water hovering above a layer of air is called Rayleigh-Taylor instability. It's the same instability that drives hot air to rise and cold air to fall. It's very ubiquitous in nature. And it's just part and parcel to doing an implosion because you have layers of material of different density that you're accelerating to, in the case of our experiments, we are accelerating our shells of material to 10 to the 14 Gs, where G is the acceleration due to gravity. So it's just enormous accelerations because we're going from a standstill to about 400 kilometers per second in a few nanoseconds. So just enormously high accelerations. And they can lead to this kind of catastrophic behavior if we don't manage it correctly. And the reason why we have to go to such crazy high velocities is we have to get the high temperatures that are needed for interesting fusion to happen. We also have to compress up the fusion fuel so that we get those collisions with the alpha particles so that the energy is trapped inside to get that explosive thermal instability. So a lot of inertial confinement fusion is trying to get a lot of conditions to happen that really Mother Nature doesn't want to happen. So we're fighting Mother Nature every step of the way.
And
Okay.
Build a Hope had asked you about increasing the amount of energy of the blue light, and I have a sort of an addendum question to that. It would seem to me that you would get a lot more energy if you increase the frequency, decrease the wavelength of the light, if you went to ultraviolet, for example.
Yeah, actually, where am I? Okay, so yeah, if we go to lower frequency, we actually could have more energy. So if say
lower frequency rather than higher frequency?
Lower frequency, we could have more
green
energy.
Light NIF.
Yeah, so green light NIF, which would be intermediate between the red and the
Yes,
blue.
yes.
That would give us more energy. I think, I don't have it here on these slides, but if we went to green light, which you can kind of see in this image here, it goes from red to green to blue. There's just a tiny section here where the light is green. I think the amount of energy in that green light is 2.7 megajoules. So intermediate between the three and.
So if you were to use a doubler instead of a tripler,
yeah,
you would probably have more energy.
Yes, we would definitely have more energy. And so you might say, well, why the heck are you using blue light then? The whole story is about more energy. Why aren't we just using red light? We can take the full 3 megajoules. And that goes back to the history of the laser program here at Livermore. The first experiments using the old facility they call a Shiva laser was in red light. And what actually ends up happening with red light, you're more prone to creating a problem that we call a hot electron problem. And you're more likely to have laser plasma instability problems. And basically, the hot electron problem is, think about surfers like at Santa Cruz surfing on the big waves. So the surfers basically try to match the phase velocity of the wave, and they can get up on their surfboard and they can take energy from the wave and accelerate themselves, and they can have a fun day. Well, electrons can do that, and electrons will do that on light, and the light actually interacting with the plasma inside the Hall-ROM. So when you have red light, you're actually much more prone to making those electrons accelerate. Those electrons accelerating then hit your capsule, your fuel capsule, and they cause it to heat up. And when you cause your capsule to heat up prematurely, it's harder to squeeze because the entropy is higher, the pressure is higher, and the problem is we have to be able to squeeze this thing up a lot before we get it hot. And we call that the hot electron problem, or the preheat problem is another jargony term we use. And so that's why we don't actually use the red light, even though we have more energy. And again, it's all about trade-offs. We would like the more energy, but we don't want the hot electron problem. And that's how we ended up with blue light, where we thought it was enough energy, but we wouldn't have as much of this hot electron problem. We wouldn't have as much of the LPI problem as the program originally did. And so there were two lasers prior to the NIF here at Livermore. Was the Shiva laser, and then there was supposed to be a Shiva upgrade, and then that actually became the Nova laser. Some of you who were here at Livermore might remember that. And then the NIF laser. So part of it has been learning over the decades about some of the compromises we need to make to try to make everything work together in this integrated system. And
so maybe you might think about the idea that I said about using a doubler instead of a tripler. The efficiency would be more, and the green light might be the intermediate between the red and the blue.
It might be a compromise. You're definitely correct. And there is another retiree who I don't know if she's part of your group. Her name is Mary Spaeth. She's a strong advocate for green light. She actually has done quite a lot of work on that. And I worked with her a bit in kind of the 2015-2016 period, because we were re-examining green light for the very reasons you're just saying. And because even at that time we recognized we probably need more energy to kind of make this work. We didn't pull the trigger on that though, but there are good rationales to examine it again. Of course, we have gotten it working finally with the blue light that's there, but it'd still be worth exploring, and there are people who are interested in looking at that. So
you have a couple of questions.
Yeah, I see some.
Ken Powell has asked about the reload time for the pellet and the capacitors, but I think that it's a one-shot deal with the pellets, isn't it?
Yeah, the targets that we shoot, this Hall-ROM in the upper right, and a good part of the arms that attach to it are completely vaporized.
Yes.
In our experiment, and certainly the capsule and everything else is completely vaporized in the experiment. So so kind of where those fingers are touching,
Yes.
everything above those fingers is just completely gone. You'll never see that again. So when we do these experiments, we basically have to insert a whole new target in,
right,
and get it filled with fusion fuel to get it to go again. Now, the rate at which we do experiments on the NIF can actually do 3 experiments a day, basically. Not generally, we don't do these type of yield producing experiments 3 times a day. We do those at most maybe once a week. Typically, but there are other experiments that go on the NIF that at the maximum rate we've ever been able to shoot is about 3 times the day. One of the issues is you have to let these lasers cool off in between, so you kind of have a cool down time before you can shoot again and not damage the laser. For us, when we do these ICF experiment, these yield producing experiments using these Hall-ROMs and these capsules, there's the fusion fuel that's inside. It actually can take 24 hours minimally to form the proper fusion fuel layer on the inside of the capsule. And let me, I don't have a picture other than this cartoon. But here, this is an engineering drawing. The capsule is not filled with the fusion fuel completely. It's hollow. And the reason why it's hollow is, again, we have to accelerate this to high velocities. And if you fill it with fusion fuel, you could never get the fuel layer to accelerate to high velocities like we want. So instead, we have a shell of fusion fuel that is kind of stuck to the inside of the capsule, and we call that the DT layer. And there's a team of cryogenic experts who basically fill this capsule with liquid and then get the fusion fuel to kind of creep up on the inside of the capsule and then freeze it in place. And then, of course, we're picky, as I said, because we're picky about not having defects that will start be seeds for instability, and we're picky about having uniformity because we don't want to cause any more asymmetry than we have to get. So they have a set of specifications on the smoothness of this cryogenic fuel and on the uniformity of the thickness of that cryogenic fuel. And if they don't meet those specs, they'll melt this layer and start over again. And we could spend like a week doing that over and over again. This team of people will spend a week basically melting that layer, then refreezing it. And there are little heaters on the outside of the Hall-ROM here that they put a little electric current in that will cause temperature gradients in both directions, and they could move the DT layer around. They can do a partial melt to try to fill in little bumps or cracks that show up in the layer. And they'll just keep doing that until either they run out of time and we're forced to shoot, or they're well within our specs and then we're ready to go. So it's quite an elaborate process preparing for one of these experiments. And of course, again, kind of those of you who are interested in fusion energy, that's one of the challenges about converting, a science experiment into fusion energy, because that would never be practical for actually energy production.
Correct.
So we'd have to figure out how to do that in a much more rapid way, without so many people involved, and with a lot more reliability. But that, that's future work. In principle, that's engineering. Enough smart people, we could, just engineering. Yes, wrong group to say that too. That's
and another question. I'll interpret another question. Are you operating in a vacuum or are you operating in an atmosphere?
Okay, so the interstitial region between the hull ROM and this capsule, that's actually filled with gas. That's actually filled with helium gas. And the purpose of that helium gas is to try to slow down the plasma that's produced on the inside of the hull ROM running inwards too quickly. So that's why that gas is in there. The target chamber itself, between the target and the lasers, you know, that's basically air. Yeah. Okay, yeah. So I also saw someone had a question about target manufacturing, which is kind of interesting. So let's get to these targets. So there are a whole bunch of components to the target here. So the central part is this capsule, and the way they make this capsule, depending on what material, again, we're using mostly diamond material or industrial diamond now. We start off with a ball of plastic, and the ball of plastic is put into a plasma coater, and the coater basically has a racetrack that the plastic ball rolls around in, and the plasma, carbon plasma, is shooting out of the coater like a sprinkler, and the carbon is floating down onto the racetrack while this pellet of plastic is rolling around. And so the pellet is rolling around and picking up carbon on its surface, and you're slowly building up the capsule kind of atoms at a time through this plasma vapor deposition process. And that builds up the capsule in layer. This is, again, kind of an X-ray image of the inside of the capsule to the outside. We're building it up in layers. You can see there's like a difference in set of color. You know, this is light gray and this is dark gray. That's actually because we specified that the inside of that capsule have a little bit of higher Z tungsten involved in the deposition process. Then it goes to pure carbon going out.
I see.
And there's a whole nother story as to why we do that. We know the high Z materials is really effective at preventing X-rays from penetrating in and preheating the fusion fuel, so that tungsten is there actually to stop X-rays from the outside penetrating through bare carbon and heating up the fusion fuel prematurely. And that's great for preventing preheat, but it also is another interface that potentially is a source of Rayleigh-Taylor instability. So it's all a matter of balancing that out. Anyway, so they build up these capsules layers at a time until they get to the requested thickness. As they get through each of these layers, they take it out of the system, they look at the surface, and they might go through a polishing step to try to smooth out any defects, and then throw it back in the coater and continue to build it up until they get the thickness that we need, that's consistent with the laser pulse that we're getting requesting, and the surface finish that we want. And of course, you know, this whole because these are engineered objects, you know, the physicists want perfect surfaces and perfect material composition. And of course, they're engineered so they don't come out perfect. So it's always you know, a matter of compromising. You know, if you want to do experiments, you got to take what can actually be made. So go ahead.
It sounds like you're spraying it. You're not doing vacuum deposition, correct?
It's plasma vapor deposition, so it is not vacuum deposition. The other capsule materials we've used, as I said, were plastic. When I say plastic, what we actually mean is GDP plastic, so it's gaseous diffusion plastic is the other material. And then we've also used beryllium capsules, which also use a plasma vapor deposition process. There have been a few cases where we tried machined capsules. So you just take a block of material and you machine out shells, and then you combine the shells together. The problem with doing that is where you actually have to take two hemispheres and combine them together. It's really hard to get the joint good. And so we generally don't do that. The other parts of the target are this hull ROM, and the hull ROM is made out of gold, or it's made out of depleted uranium that's coated with gold. And those are coated on a mandrel. And again, the mandrel is kind of pulled out after the coating is made, and then the capsule is placed inside, suspended on these plastic membranes that we call the tent. These materials are actually called form bar, FORMBAR. It's a type of plastic. What's interesting about that material, again, another jargon term we use is the tent. These are like two drum heads. So the hull arm is actually made in two halves. So it's split the hull arm in half, and imagine taking like saran wrap and covering each half of the hull arm, and then trapping the capsule in between these two membranes of plastic that are like drum heads. So that arrangement we call a tent. What's interesting about the tent is the thickest it was about 100 nanometers thick back in like 2010. We're now regularly shooting tent thicknesses of about 30 to 45 nanometers. We've gone as little as 15 nanometers, which is just kind of a handful of atoms. So these are really gossamer thin membranes of plastic that are suspending the capsule in the center of the hull arm. So that's quite an engineering feat in itself.
So that's what's holding the capsule. In fact, there was a question as to what holds the capsule in the center.
Yep, it's these gossamer thin drum heads of foam bar plastic that hold it in the center.
Right.
And then you can barely see in this image here, there's a little tube that enters through the side of the capsule, and that goes through the side of the hull arm, and that goes through the side of the capsule, and that's how we get the fusion fuel in and out in liquid or gas form. And so all of this is put together basically by a set of engineers / artisans who assemble the pieces up into a final target.
And then,
well, those fill tubes have gotten amazingly small too, hasn't
yeah,
that?
that's it. There's a whole story behind the fill tubes. As I try to imply, all of those engineering features cause seeds for instability. So this, when you look at this model here running, okay, these perforations here, that's actually from contact with that gossamer thin tent, and as you can see, they get amplified. So that's been a challenge for us, and that's why we kept making those tents thinner and thinner and thinner. We also looked at other ways of holding the capsule that none of them have actually panned out yet, but we did look at it. And then here on the side, you can see this one feature plunging in. That is the fill tube perturbation. And again, it gets amplified in an implosion where you're not as well controlled as what we're doing today. But because of that feature, we've actually had to, well, we tried making the fill tubes as small as we could make them practically and still fill the capsule up with fuel. So the fill tubes actually are about 100 microns in diameter here at large radius. They narrow down, originally they narrowed down to a 10 micron radius, and that's where they entered the capsule. And again, remember, like 100 microns is about the thickness of a human hair. So 10 microns is a 1/10 the thickness of a human hair. But because of the perturbations that we were seeing in the experiments, using those large, what we call large fill tubes today, and the simulations, which showed, yeah, that's enough of a perturbation to cause a jet, a problem for us. We, the engineering team, proceeded to look at smaller and smaller fill tubes. So we went from 10 micron fill tubes to 5 micron fill tubes. And in that period between 2015 and 2018, most of the experiments were using 5 micron fill tubes. And then we went to 2 micron fill tubes. And most of our the 2 record experiments that we talked about in this talk, or highlighted in this talk, used 2 micron fill tubes. And I think for the last 2 to 3 years, almost all of the experiments we've done have been using 2-micron fill tubes, but these are, we get these fill tubes from a in vitro fertilization glass manufacturer that basically takes glass tubes, and then they are able to draw it out into these, tiny filaments, and their primary customer is to make these tubes for in vitro fertilization, but they draw them out for us too. They're extremely fragile, as you can imagine, and they're actually one of the reasons why targets actually might fail before we even get to do an experiment. And that's been one of the practical frustrations is, again, from the physics point of view, we want all of these engineering features to be as small as possible because we want this ideal physics situation. But reality says, there's only, the engineers can only make it so small and not have it fall apart on us. So part of our job is kind of trying to find the balance between the engineering and the physics to kind of make this work. Again, that's kind of why it took us so long. Actually, if you look here on the right, I forgot to mention this. On the right of this image that I have up on the screen, you can actually see the fill tube. And what is being shown here in this particular case is you have the fill tube coming straight into the side of the capsule. And then here's the fusion fuel on the inside, that DT layer that I talked about before. And what we were noticing is actually as we cooled the capsule, they cooled the experiment down before shooting it, that capsule would bend. And sometimes it would break. And this in particular was the 2-micron fill tube. So, there's just a whole bunch of practical challenges that are involved in fielding these experiments. And that's why it takes such a large team of people to kind of make it work.
One of our engineers is really keen to know how you do your simulations. What programs or coding do you use?
Oh, yeah, that's a whole story in itself. So we, those of you who know Livermore, Livermore kind of made its name in the national security arena by having these very large multi-physics codes that have been developed over many decades by large teams of computational physicists. And the codes, have evolved over time. The names of the codes that we use are code named LASNEX, which is one of the older codes. This simulation here that I showed during this talk, this comes from a code named Hydra. And we also use other code, another code called Aries. These codes are multi-physics, what we term radiation hydrodynamics codes. So they're basically fluids dynamics codes, but they have the physics of radiation transport, both X-ray and neutron physics in them. They have magnetic field physics in them, and laser deposition physics in them. And so it there's some analog at some core level. They're kind of like hydrodynamics codes with all this extra physics put in. They're written in a variety of different languages. The older ones, basically are written in Fortran. The newer ones are written in C. I think Hydra is basically a C or C++ based code. And again, they've been developed over many decades by large teams of people, so that they're not available outside laboratories like Livermore or Los Alamos. Sometimes we'll have university guests who can actually run them on our systems, but they're not generally available outside. Is that enough of an explanation?
Yes. And then the last question that I see is talk about how this might eventually evolve into practical power source.
Yeah, so turning this into a practical power source requires a few steps. Let's see. The physics step is we have to get the fusion gains up. So right now, we're getting a gain of 1.5, which means we get 1.5 times more energy out in fusion as we shot into the target. That nowhere near makes up for the energy that the laser consumed. So the two things we have to do there are we have to increase the fusion performance of our targets, increase the fusion gain, and that involves solving that compression problem and perhaps continuing this tactic of making the targets bigger and bigger to some degree. We have to make the laser more efficient. The NIF laser was built on 1990s technology. It's only 0.5% efficient in energy. I'm told by our laser experts we can build lasers today that are 20% energy efficiency, 20% efficient. So if we can get the laser energy efficiency up and get the target gain up, pretty soon you'll be in a position where the fusion yield actually can exceed the amount of energy that the facility consumed, and that's a necessary step. The other step that's required for us is to make these targets more practical. So these targets are very elaborate things. They're very fragile. They don't make a lot, it takes a team of scientists to set it up. That wouldn't make sense for a power plant. So we need to make targets that are compatible with the physics needs, but are also less fragile and maybe a little less elaborate, because these targets are expensive and they take a long time to produce. And you would need very cheap, robust targets that you could shoot, just millions of, and not have it cost a fortune for fusion energy to be economically viable.
Yeah.
The other aspect of what we call inertial fusion energy is that we have to be able to do what we call shots. Our experiment we call a shot. You can't just do one a week, because that wouldn't make any sense. So what we have to be able to do, the projections are we'd have to be able to do a shot, 10 times a second. So we're going from a rate where we're doing an experiment a week to basically doing a shot 10 times a second for practical fusion energy. And the reason why is, each one of these is a little explosion and they liberate energy, but then it's gone. And then you shoot in another target, you blast it with the laser, it liberates energy, you harvest that energy, and then it's gone. For an inertial fusion energy system that to make sense, you have to kind of do it at a rate of 10 hertz, roughly speaking. And we're not in a position to be able to shoot targets of this or any other type at that rate. So that is a significant engineering problem that would need to be addressed, and there are people working on that. It's there are designs for inertial fusion energy plants that exist. They were waiting for kind of this moment where we actually kind of prove the physics to kind of get momentum going, and so that's kind of the stage we're in now. So people are looking at this again.
NIF was kind of conceived to be, easily convertible between whole realms and direct drive. I suspect that's not so easy to do.
Yeah, actually, yeah, that's a good point. In principle, it should. We do. Our facility does do direct drive experiments, and for those of you who don't know what that terminology means, is it basically throw out the Hall ROM here and shoot the capsule directly with the laser, and there are physics pros and cons to each approach. Livermore chose the approach of using the Hall ROM. A laboratory in Rochester called the Laboratory for Laser Energetics primarily works on direct drive. We have done direct drive experiments here as well. The issue with that, being true in principle, but maybe not being true in practice, is this configuration of the laser beams here, which you can kind of see. Most of the laser beams, go back to this image here. For our Hall ROMs, the laser beams enter at the top and the bottom, and that's great for Hall ROMs. The laser was kind of designed, our laser system was kind of designed to be more adaptable to Hall ROMs. So you can see most of these lasers enter at the top and the bottom, and the waist of the target chamber is free of lasers. And that's great for indirect drive, where the lasers enter the target from the top and the bottom, and then we have diagnostics arrayed around the target chamber to actually do measurements. For direct drive, again, because of the same symmetry physics that I tried to explain earlier, For direct drive, where you're shooting the capsule directly with the lasers, you want a uniform illumination with the lasers, but you don't get that here at NIF because there are no lasers on the equator of the target chamber. So although we do direct drive experiments, they're kind of compromised because we're only hitting the capsule at the top and the bottom. And to reconfigure this part of the NIF laser to do what we call spherical direct drive experiments would be a considerable amount of re-engineering of the system, and there's a considerable dollar figure associated with that, and no one has kind of pulled the trigger on that yet. So
much work in the last 10 years has been, understanding the whole realm of physics, right, and the cross-beam coupling and everything, right? And one way of looking at it is those problems kind of go away if you have, a perfectly symmetric direct drive system, but one could also argue there'll be a whole nother realm of physics problems.
Yeah, so yeah, that's the wise statement. You think you're making one thing better, you're often usually making another thing worse in our business. We kind of already know what that other problem is. So while what you just said is right, controlling symmetry with a spherical direct drive setup is probably easier. What we do know will make worse is the Rayleigh-Taylor instability growth. And that's because the way energy is deposited in a direct drive implosion is different than in a Hall ROM. In a Hall ROM, we convert the laser energy to X-rays. The X-rays relative have a fairly long mean-free path. So the ablation front on the outside of the capsule has a fairly long length. And that tends to be more favorable for controlling Rayleigh-Taylor instability than what happens in direct drive, where in direct drive you shoot the lasers directly at the capsule. The heat isn't transferred to the capsule, or the energy is not transferred by X-rays, it's transferred by electron conduction. And electrons have a very short mean-free path because they collide with stuff readily. So the ablation front in a direct drive capsule is much steeper than an X-ray driven capsule. And a steep ablation front is much more prone to Rayleigh-Taylor instability than a gradual ablation front. And so that is one of the significant concerns with the trying to do direct drive is controlling an already difficult to control Rayleigh-Taylor instability process at the ablation front. So again, it's all trade-offs, and we got something to work. So it's although we should still consider all of the different options before saying that we know what the right answer is.
It's really been great to hear you go through this, because you've been very, very open and forthright about all the details, including all the pitfalls.
Yeah, that's nice of you to say. Well, it's a story of falling down a lot, but eventually getting back. And I think it's kind of an important story. It's we didn't know all the answers, and it didn't work right out of the box, and that being allowed to actually go through that learning process is part of the success. It's
All right, well, thank you very, very much for your talk.
All right, well, thank you for your interest, and I appreciate being invited and telling you our story.
Thank you very much.
Okay, have a good night.
Thank you. Good night.